Okay, let's look at spanning sets. Uh, if S is a collection of vectors that's a subset from a vector space V, then S is a spanning set of V if every vector in V can be written as a linear combination of vectors in S. So if we go back up here, this was a spanning set of R2. This one we saw was not a spanning set of R2 because you can't get everything in R2, just the stuff on this line. And we saw that this was a spanning set of R2. Uh, Let me throw one more example up here before we look at the ones below. The set 3, 7. Is that a spanning set of R2? No, because that's only a set with one vector, 3, 7. It's going to look something like that. And so linear combinations of that are just multiples of it. So all you can get from this is just points on that line. So this is not a spanning set of R2. So down here, I've got several examples. One thing I want to mention, though, first is in order for something to be a spanning set of R2, it's got to have at least 2 vectors in it. If you've only got one vector, all you're going to get is a line. So let's look at a few different examples. Examples of spanning sets of different vector spaces. So this set spans P2. And if you think about it, P2 is the set of all polynomials of degree 2 or less. So if you just wrote out an arbitrary polynomial of degree 2 or less, it would look like that. And you can definitely get this by taking linear combinations of these. I mean, it's practically written right there. You'd use A for your coefficient of x squared, B for your coefficient of x, and C for your coefficient of 1. And that'll get you any quadratic polynomial you want. It'll also get you any linear polynomial by picking A to be 0. And if you pick A and B to both be 0, then it'll get you any real number, which you can think of as a polynomial of degree 0. All right, this next one. This right here spans R3. Well, let's see how. Here are my axes, x, y, and z. If we look at these, 0, 4, 0, that sticks out 4 units along the y-axis. This sticks out -1 unit along the x-axis, so back this way. And then this last one sticks out 11 units along the z-axis. I'm not going to worry with making this exactly to scale, but by taking linear combinations of those, you can go whatever direction, you can go in each direction whatever length you want, so you can get anything. Okay, this next one, this set spans M22 because you can get any 2x2 matrix. You get this matrix by choosing these for your coefficients. And in general, you can get the matrix A, B, C, D by picking these as your coefficients here. So those do span M22. You can get any 2x2 matrix you want by adding multiples of those guys together. And then finally, this last one says this set spans R2. Okay, this one's kind of interesting. If we draw out R2, then this guy is the unit vector, means length 1 in the y direction. So you've got this, then you've got this, this way. And if I stopped here, this is already enough to get everything in the plane, because we can easily take linear combinations of these guys and get anything. So that's already enough to span the plane, but we've got another vector here that points up to 1, 1, and it's fine to have that in there too. It's not necessary to have a third vector, but we've got it, and we'd still say that this set spans the plane. Now down here we've got several examples that are, well, non-examples of spanning sets. I actually want to come down here and talk about this from 2.1 before we do the non-examples. In order for a set S to span R2, it has to contain two non-zero vectors that don't lie on the same line. And that makes sense, because if you've got R2 here, if you only have one vector, then it's going to span a line, unless it's the zero vector, in which case it'll only span the origin. But you have to have a vector to get one line, and then you have to get a vector to get another line. So you have to have at least two non-zero vectors. In order to for a set to span R3, you have to have three non-zero vectors, and they can't lie in the same plane. So let's go back up here and look at these examples. Okay, this first set here, this does not span R3 because it's only two vectors. If you have two vectors, I'm going to do an example here. If you have two vectors in R3 and one of them is pointing in some direction and the other one is pointing in a different direction, what you can get out of those is anything that lies on that plane between them. You can think of it like this would get us anything that lies along this line with the pencil, and adding this on would get us anything in the plane. And you could do it in this direction and get this exact same plane. My cat is interested in this. So if we only have two vectors, those together will span a plane, but they won't span all of Rn. All right, now what about these guys? 131, 262, and 410. That says these do not span R3. The reason for that is what you've got is one vector pointing out in this direction for 131. 262 points out the same exact direction, just twice as far. So together those get you a line. And then when you stick 410 on here, I'm just drawing it in some arbitrary direction. It's not on the same. It's not the same line, but those three things all lie in the same plane. So those span a plane, but they don't span all of R3. Now this next one is sort of the same thing is going on. It says those don't span R3. It's not obvious to me when I just look at this one that they don't span R3, but they don't because all three of them lie in the same plane. Here's how you can see that. I'm going to take these and stick them into Octave, and we're going to see that one of those is a linear combination of the others. Here's how I'm going to do it. I'm going to stick in a matrix. I'm calling it MT for transpose, because basically what we'd want to do is set up C1 times 4, 5, 1 plus C2 times 1, negative 4, 7 equals 3, 2, 3. Now, it's easier for me to type these in like that instead of having to go through and convert them all into columns. So that's not quite what we want for our system. You know, we want the system 4, 5, 1, 1, negative 4, 7, 3, 2, 3. So I'm going to make M be the transpose of MT. And so that's the matrix we want. If you take this and row reduce it, you get this. And what this tells us is this third column here is 2/3 of the first plus 1/3 of the second. So let's check that on one of them. 2/3 of 4 is 2. Wait, no, 2/3 of 4. No, 2/3 of 4 plus 1/3 of 3 gives me 6, 7, 8, 9 over 3, which sure enough gives us 3. So I'm getting a little bogged down in the computation there, but the idea here is these three vectors, they all lie in the same plane. All right, and this next one we can't really visualize, But in order to span R4, you have to have 4 vectors, and this only has 3. So those don't span R4. So let's see, this bit down here, we already talked about R2 and R3. But in general, in order for a set to span Rn, the set must contain at least n vectors that are linearly independent, meaning that none of them are linear combinations of the others. We'll define that in a minute. But that's what's going on here. In this case, for R3, we only had 2 vectors here, so that's not enough. For this one, we had 3 vectors, but they weren't linearly independent. These two, one's a multiple of the other. And for these aren't linearly independent because this is a linear combination of those. And for R4, we just don't have enough vectors here. All right, so we'll talk about linear independence and linear dependence in the next video.